Chemical bonding 6. Intermolecular forces. The essential idea is the physical properties of molecular substances result from different types of forces between their molecules. Nature science. We obtain evidence for scientific theories by making and testing predictions based on them. For example, London or dispersion forces and hydrogen bonding can be used to explain special interactions. For example, molecular covalent compounds can exist in the liquid and solid states. To explain this, there must be attractive forces between their particles which are significantly greater than those that could be attributed to gravity. So, why do molecules stick together? Why do some things mix and not others? Why do some substances become solid at room temperature and others are liquids or gases? Why do some things have high boiling points and others very low boiling points? Why do some smells travel very quickly? Well, it's all about the forces that hold molecules together. Forces of attraction occur both inside and between molecules. Inside a molecule, there are intramolecular forces, and these occur between the positive nucleus and the bonding electrons. You can see here, if this was a water molecule, there's a force holding the hydrogen to the oxygen. Or here, let's just say it's chlorine. You've got a force holding the chlorine atoms together. It's a bond, this chemical bond between atoms. Between two molecules, there are intermolecular forces, which occur between the positive region on one molecule and the negative region on another molecule. Again, we're using water as an example, and you can see the hydrogen has a positive dipole, and the oxygen here, negative dipole, and so a bond forms here between the water molecules. Different forces are broken during chemical and physical reactions. The intramolecular forces are broken and formed during chemical reactions. And you can see here, let's just say it's water again, two water molecules reacting under extreme conditions to give an oxygen molecule and a hydrogen molecule. These bonds are broken and new bonds are formed between the atoms. New substances are formed during chemical reactions. When intermolecular forces are broken during physical reactions, for example, when things melt, when things boil, when things dissolve, the bonds are far weaker than the intramolecular forces. So not as much energy is required for these bonds occurring between the negative dipole and the positive dipole to break, giving free molecules. And this, you can see, is the same substance. Say if that was a hydrogen, this was a hydrogen, and this is an oxygen. You've got the same thing over here. It's the same substance, but in a different state. We will only look at intermolecular forces between covalent molecules from here on. And there's three types. The first, dispersion or London forces. Second, dipole-dipole forces and dipole-induced forces. And hydrogen bonds. The first two are considered under the umbrella van der Waals forces. All intermolecular forces are a type of electrostatic force. The types of intermolecular forces, IMFs, that form between molecules of any substance depends on the polarity of the molecule. Quick review. Which molecules are polar? Which molecules are not polar? Test yourself. Do it now. Press pause and check which ones, see if you can remember which ones are polar and which ones are not polar. Well done if you got them correct, and I know that you did. So, dispersion or London forces of attraction. An electrostatic force of attraction between all types of molecules. All molecules have these dispersion or London forces. It's the only type of force that holds non-polar molecules together. Remember that non-polar molecules don't have any dipoles. They have no regions of partial charge. The electrons in a non-polar covalent molecule are equally distributed around the molecule, so no permanent dipoles form. But what holds them together? What would hold iodine together? Iodine's a solid. How can electrostatic forces form between non-polar molecules if there are no charged areas? Well, there's an interesting phenomenon that occurs in molecules known as the temporary instantaneous dipole. An induced dipole and an induced dipole. You can see this diagram here. We've got molecule 1, electrons in constant random motion. So at any one instant in time, you might have a temporary positive dipole and a temporary negative dipole on either side of the molecule. This here could then induce a similar situation on a neighbouring iodine molecule. As the molecule 1 approaches another molecule, it induces a dipole on that molecule, and a weak electrostatic force of attraction would hold the two together. So this here, these electrons here, are inducing a dipole over here. The delta negative, or the negative dipole, is repelling these electrons to move to the other side, which induces a positive dipole here, and then you get a bond forming, a dispersion or London force bond. These dipoles are temporary and are constantly being formed and broken. This is why London forces tend to be weaker forces. Dispersion or London forces are generally weaker intermolecular forces. However, their strength does vary, and it depends on the number of electrons in the molecule. The more electrons there are, the greater the number of dispersion forces that form. Let's consider these non-polar halogens. In chlorine, which has 34 electrons, we have fairly weak dispersion forces. And then in iodine, which has 106 electrons, we have the strongest dispersion forces. Chlorine has a boiling point of 238 Kelvin, bromine 332 Kelvin, and iodine a boiling point of 457 Kelvin. Chlorine is a gas at room temperature, bromine exists as a liquid, and iodine exists as a solid at room temperature. And the only difference between the three is the extent of dispersion or London forces that are occurring, and this is directly to do with the number of electrons on the atoms. Dipole forces of attraction. An electrostatic force of attraction between opposite dipoles on two molecules. And example 1 here, we see hydrogen chloride, and you can see that there is a polar covalent bond between the hydrogen and the chlorine atom, which is making a dipole moment on the molecule, and so we have a positive dipole and a negative dipole on each molecule. The negative dipoles are attracted to the positive dipoles, and this is a dipole-dipole force of attraction. You see the same thing happening down here with nitrogen trifluoride. The positive dipoles is on the nitrogen, and the negative dipoles on the very electronegative fluorine atoms. So they're forming between polar covalent molecules that have permanent dipoles. These aren't the same as the temporary dipoles that set up in the London or dispersion forces. Let's compare the effect of dipole-dipole forces of attraction on the boiling point of two molecules with the same number of electrons and similar molar mass. So we've got ethane here, and we've got fluoromethane over here. So the ethane has 18 electrons and it's 30 grams per mole, molar mass, and the fluoromethane, has 18 electrons and 34 grams per mole. This is a non-polar molecule. The fluoromethane is a polar molecule because of the electronegative fluorine. This has dispersion or London forces only, so temporary dipoles are set up, and this has dispersion forces and dipole-dipole forces. And have a look. The boiling point of ethane is 185 Kelvin. The boiling point of the fluoromethane is a full 10 Kelvin higher because of the added effect of the dipole-dipole forces. When molecules have similar number of electrons, the presence of dipole-dipole forces will increase the overall strength of the intermolecular forces, and the boiling point will then increase. Let's compare the effect of dipole-dipole forces of attraction on the boiling point of two molecules with very different number of electrons and molar mass. So, hydrogen chloride, 18 electrons and it's 37 grams per mole. Hydrogen iodide, 54 electrons and 128 grams per mole. Both are polar molecules. Both have dispersion forces and dipole-dipole forces. And the boiling point difference is quite large, you can see here. Okay, hydrogen chloride, 188 Kelvin. Hydrogen iodide, the boiling point is 238 Kelvin. So, when polar molecules have very different numbers of electrons, or molar mass, the effect of London dispersion forces on the strength of the intermolecular forces is greater than the dipole-dipole forces. Dipole-induced dipole forces of attraction. Some polar molecules can induce a dipole on a nearby non-polar molecule. This sets up a dipole-induced dipole force of attraction. What? Let's look at an example. We've got the non-polar oxygen gas molecule. It's symmetrical, it has a symmetrical electron cloud and it has no dipoles. However, if a water molecule were to come into the proximity of the oxygen molecule, then the negative dipole on the oxygen induces a dipole on the oxygen. It repels the electron cloud, which moves further away over here, forming a positive dipole here, and then there's a force of attraction between these two dipoles. You can see how the electron cloud is distorted, forming the temporary dipole. Next we have hydrogen bonds. Hydrogen bonds are a special case of dipole-dipole forces, and they are strong intermolecular forces. So let's look at molecule 1 and molecule 2. What's going on? Well, first of all, X here and X here have to be fluorine, oxygen or nitrogen for it to be a hydrogen bond, for it to be considered a hydrogen bond. And you can see we have the positive dipole on the hydrogen and the negative dipoles form on the fluorine, oxygen or nitrogen that have one or more lone pairs. So hydrogen bonds involve an electrostatic force of attraction between a strongly positive dipole on a hydrogen atom in certain molecules and a lone electron pair on a strongly negative dipole on the fluorine, oxygen or nitrogen atoms in another molecule. Examples of substances with hydrogen bonds. Water being the most famous, I suppose. You can see the hydrogen, the the positive dipole on the hydrogen and the negative dipole on the oxygen with two lone pairs forming a bond. In ammonia, we have the positive dipole on the hydrogen forming the hydrogen bond with a lone pair of the negative dipole on the nitrogen. And here we have hydrogen fluoride, the negative dipole on the fluorine with its three lone pairs and the positive dipole of the hydrogen. Substances with hydrogen bonds, methanol. Here you can see the oxygen atom with the negative dipole forming a hydrogen bond to the hydrogen on the hydroxy group of another methanol atom, hydrogen oxygen being having a positive dipole. And here you can see the negative dipole on the nitrogen of the ammonia molecule forming a hydrogen bond with the hydrogen with a delta positive, with a positive dipole on this water molecule. Here's some examples of substances without hydrogen bonds. The intermolecular forces in these substances are weaker dipole-dipole forces. They're not hydrogen bonds. Why not? Well, here the chlorine is forming a dipole with the hydrogen from the hydrogen fluoride. This is capable of forming hydrogen bonds, but the larger chlorine atom is not able to form the hydrogen bond, and more on that in a bit. And over here, the fluoromethane, you see this carbon here, the hydrogen isn't bonded directly to the fluorine, it's bonded to a carbon. So you're going to get a weaker polar covalent bond, weaker dipole, so this positive dipole is too weak to form a hydrogen bond. Why do fluorine, oxygen and nitrogen contribute to the formation of strong dipoles? Okay, well, the fluorine, oxygen and nitrogen have high electronegativity values of 4, 3.4 and 3. The hydrogen atoms bonded to these acquire a strong positive dipole. So over here we're getting a strong dipole on the hydrogen because it is bonded to an atom with a high electronegativity. So a strong negative dipole forms on fluorine, oxygen and nitrogen because they are so electronegative, and a strong positive dipole forms on the hydrogen. The electrons obviously shift over towards the fluorine, oxygen or nitrogen side of the molecule. They have lone pair electrons in the second energy level. Fluorine, oxygen and nitrogen all have lone pair electrons in the second energy level. The lone pairs are on a small volume and thus they have a high charge density. And if you think back to the last slide, the chlorine didn't have this high charge density, okay, and that's why there wasn't a hydrogen bond forming. The strength of hydrogen bonding in these molecules. We've got ammonia and we've got water. The boiling point of ammonia is 240 Kelvin. The boiling point of water is 373 Kelvin, so there's quite a large difference. Both have hydrogen bonding. So how would we explain these boiling points? Okay, this is quite verbose, so I'll read it as clearly as I can. In hydrogen bonding, it is the delta positive hydrogens that is attracted to the lone pairs of the electronegative nitrogen, oxygen or fluorine atom. The oxygen atom in water has 2 lone pairs, 1, 2, while the nitrogen atom in ammonia has only 1 lone pair, over here. This means that each water molecule can form double the number of hydrogen bonds than an ammonia molecule. More hydrogen bonds means stronger intermolecular forces, which means a higher boiling point. Let's consider the trend in boiling points in the hydrides of group 14, 15 and 16. Let's start with group 16. Okay, first of all, water here has quite a high boiling point. And it has a high boiling point because it's the only substance with hydrogen bonding, which is the strongest intermolecular force. The other 3 substances all have dipoles forces as the strongest intermolecular forces. And also, as the mass of these molecules gets larger, the dispersion or London forces increases. And so that's why we're getting a gradual increase for these 3. Next, group 14. All of these are non-polar molecules. Therefore, the strongest intermolecular force here are the dispersion or London forces. And that's why we're getting the gradual increase in boiling point as we have an increase in the number of electrons available for the dispersion of London forces. Finally, for group 15 over here, again we've got an outlier here. It drops down before increasing, and that's because, as we know, ammonia can have hydrogen bonding, which is the strongest intermolecular force. The other three do all have dipole forces as their strongest intermolecular forces, but it is as the mass gets larger, there are more electrons available, and so it is the dispersion or London forces which accounts for the gradual increase in boiling point for these three. Thank you very much. I'll see you later.